All right. So there's no audience again, but to be complete, I'm going to do this summary, and then I'm going to place it on YouTube, right? So in the previous week and this week, we have covered the characters of representations. So these are really the most important properties of a representation. Basically, a representation is a set of matrices. So to identify the representation, we have to compute these matrices. But character of that representation is actually a simpler function that enables us to identify the representation and do some certain calculations with it. I guess I'm going to show you. So there, in the meantime, I'm going to show the all important properties. So as usual, we are going to talk about finite groups. For infinite groups, we cannot do this because of some certain difficulties. So for finite groups, so let's say that A is a representation, any representation at all. So it's basically a function from the group to the matrices, right? So the character of that representation is basically defined as a trace of the corresponding representation matrix. So I'm going to talk about the trace in here, but in any case, this is a number. And so as a result, you can think of the character as a function from the group to the complex numbers, right? So it's a number, but I mean, for each element of the group, you associate a different number. And, you can actually think of it like that. Okay? So it's the trace of these matrices. Why the trace of a matrix is useful, we will see. So first of all, let's talk about the trace. So I'm going to use a yellow color for that. So the trace of a matrix is defined as, trace of a matrix A is basically the sum of the diagonal entries, right? Sum of the diagonal entries. So if I consider this matrix like that, right? The first index is the row index, and the second one is the column index. So as a result, in the first row, for example, the first number is going to be the same, and so on. The diagonal entries are the entries where the row index and the column index are the same. So as a result, A11 and A22 and so on. So we are basically summing over all the diagonal entries. So that is the definition of the trace, right? It has some nice properties. So the first property is that, well, basically the trace of the product of two matrices is the same as the trace of the product, but in the opposite order, right? So trace AB is the same as trace BA, and this is actually quite easy to show because, well, trace AB is essentially is the sum of the diagonal entries of the AB product. But I can write down the summation in terms of the matrix elements like that. So that's Aij, Bji. So sum over J gives you this entry in here. And now I can actually change the places. So I can write this thing down as Bji, Aij. But if I carry out the I summation first, then, that's basically the sum over the J index of BA matrix product and the JJ matrix element, so therefore that's equal to the trace of BA. Right? Trace of AB is the same thing as trace of BA. Right? That's an important property. But sometimes it's confusing, so some people think that, well, under a trace sign everything commutes. That's not really the case. It's actually what we call as the cyclic property. Cyclic property. So that actually tells you that if you have, like, I don't know, a set of matrices like A, B, C, D, E, D, E, for example, 5 matrices are multiplied, I can essentially move one of these matrices to the end. That's what it says. So I can therefore write this thing down as B, C, D, E, A product, right? We have to understand it like that. Okay. Another property is that similar matrices have equal traces. Equal trace, right? So just remember this. A is similar to B means that It's the same thing as saying that there is an invertible matrix S where after a similarity transformation, B is converted to A like that, right? So because of that, the trace of A is the same thing as trace of SB as inverse. And now I can use the cyclic property, and then therefore this trace is the same as this one, but that's equal to identity, so therefore that is equal to the trace of B. Okay? So two similar matrices have the same trace, right? Because of that, I can do this. So if your matrix is diagonalizable, A is similar to a diagonal matrix where the diagonal entries are basically the eigenvalues of the matrix, right? So let me, I don't know how to do this. So this is a diagonal matrix. Okay, so if it is similar, then therefore the trace of A is equal to the sum of eigenvalues. All right, we can also think of it like that. So even if the matrix is not diagonalizable, we can make this identification because we can define the eigenvalues as the roots of the characteristic polynomial. So let's also talk about the characteristic polynomial. So P lambda for a matrix A, characteristic polynomial of is basically the determinant of lambda times I minus the A. In any case, if this is an n by n matrix, this is an nth order polynomial. So I don't know, I mean, let's just say it like this, right? So there's this term in here. The first term is lambda to the power n. Next term is something like that, and so on. Right? Let me write it down like that. So it appears that this C1 in here is really the trace, actually. And the last term is, sorry about that. So I'm going to write minus 1 to the power n Cn in here, so because I define it like that. The last term is the determinant of A, right? So the trace is basically the sum of the eigenvalues. So, I mean, sorry about that. So since you can actually think of this polynomial as the product of this lambda minus the eigenvalues, lambda minus lambda n. So the trace is the sum of the eigenvalues, and the determinant is equal to the product of the eigenvalues. Right? So these are like two invariants of the two particular invariants of a matrix, which doesn't change under a similarity transformation. So the whole characteristic polynomial doesn't change under similarity transformation. And so as a result, you can think of these coefficients in here, all the other coefficients as some other invariants as well. So the trace and the determinant are the two known, the most famous invariants in a way. But in this place in here, in this topic, the trace is more useful. Okay. So I think this much of the description about the trace of a matrix is actually enough. So in our case, of course, we have a set of matrices. We don't have a single one. We have a set of matrices. By using the property of the trace, we can actually talk about some certain properties of the character. Okay. So I'm going to do this as I said quickly. So as a result, I'm not going to go. I'm not going to show a detailed proof. First of all, equivalent representations have the same character. Equivalent representations have the same character. So if a representation A is equivalent to another representation B, so this then implies that implication in here, the character of A is equal to the character of B for all group elements. So let's say for all G in the group. Okay. It turns out that this implication is also valid in the opposite direction as well. So if two representations have the same character, you can show that they are equivalent to each other, right? So the analysis that we are going to do is going to be a proof of that, but I'm not going to explicitly show this, right? I'm not going to explicitly show how we can do this similarity transformation. So why, right? Because equivalent representations are basically this. I mean, there's a similarity transformation where the corresponding matrices are similar, actually. Right? So since similar matrices have the same trace, therefore the equivalent representations have the same character. Now, that's actually a nice simplifying feature because equivalent representations are different; they are not equal. But we have said that they are really the same representation, right? So somehow, if I have a representation, but if I choose the basis of my vector space in a different way, then my representation matrices would actually look like the other representation. So equivalent actually means the same thing. So yeah, even though they are the same operators, but they actually look different because I'm using different matrices, but they're really the same. So the character of the representation is actually a nice simplifying feature. So as a result, without doing much complicated calculations, I can actually understand if two given representations are equivalent or not. All right, so as a result, this is the nicest feature. Second one is this, so let's also do this. So if A is, let's say, is a direct sum of many representations, especially, I don't know, yeah, let me just write it down like that, right? So it's just a direct sum of E and C, which means that the A of G is actually a matrix like that. Right? There is a block in here where the matrix is BG, and there's another block in here where the matrix is CG, and we have zeros in here. In that case, the trace is basically the trace of this matrix and plus that matrix. So therefore, the character of A is equal to the direct sum of the character of B and C. Okay. So as a result, for the direct sum, therefore, the characters are really summed. And in general, if A is a, I don't know, I mean, let's say that I have representations U1. These are irreducible representations, let's say. U1 is repeated M1 times, and U2 is repeated M2 times, and so on. Let's say dot, dot, dot in here. In that case, the character of A is equal to the sum over and mu times the characters of these representations. Then, right? So there's a then in here. Okay. So as a result, if a given decomposition is, if a reducible representation is decomposed in a particular way, I can actually see the same kind of decomposition in terms of the character. So the character of the representation is a linear combination of these irreducible characters, right? Okay, so basically we identify a given decomposition by solving this problem, right? We just solve a linear algebra problem. Like we will identify the irreducible characters of irreducible representations, and then by knowing the character of the actual representation, I can find all of these coefficients in here and then do all the interesting stuff. Okay. Another thing in here is this. So it's the conjugacy relationship. So let's just remember the conjugacy relation in the group. So that means we say that two elements G and H are conjugate if, let's say, there is an element in the group such that G is equal to KH, K inverse, for example. In any case, this is actually an expression that looks like a similarity transformation, but it is not similarity transformation because this is actually in an abstract group, right? However, if I express this in terms of the representation matrices, so all of these three elements have representation matrices. Now, in that case, well, that's a similarity transformation. So this basically tells you that the conjugate elements have similar representation matrices. Okay, and the similarity transformation is given like that. So as a result, so we are going to say that conjugate elements have equal characters. Okay. So if G is conjugate to H, then this implies that character of G is the same as the character of H. Right? We don't have the opposite implication in here. So there's like trivial representation, for example, where all the characters are equal to each other, right? That's not really what happens. But the character, we have said that the character is actually a function from the group to the complex numbers. But this basically tells you that this function is actually constant. It doesn't change on a conjugacy class. So therefore, I can actually think of the character as a function from the conjugacy classes to the complex numbers, right? That's actually a better way of viewing this. And so that's the point of view that we are going to use, all right? As a result, I'm just going to use some kind of a new notation in here. So I'm going to call this like, I'm just going to show the conjugacy classes by CI notation. So these are the, let's say that CI is the ith conjugacy class in the group, right? So I'm going to call Ni as the number of elements of the group, number of elements of the conjugacy class, right? So let me use CI like that, right? So I'm going to use this concept in here. So I'm going to say NC as the number of conjugacy classes. So that means this I index actually runs from 1 to NC. Okay. So therefore, I can think of this character as a function from the set of numbers from 1 to NC to the complex numbers, right? So therefore, I'm going to define this. So chi-IA, I'm going to define this as the character of any element, right? For any element G of the ith conjugacy class, right? I'm just going to define it like that. Okay? So let's say I'm going to define it like that. So that, right? So I would then think of the character as like a function of the conjugacy classes. So I'm going to use mu as the muth irreducible representation. And I'm going to use chi mu as the corresponding character of mu. And I'm going to use the same kind of notation, right? So chi mu I and chi mu G, right? From time to time, I'm going to think of this as a function of the character, function of the conjugacy class. And sometimes I'm going to think of the conjugacy, I'm going to think of the function of the group element. Okay, let's see. Right, that's it. I don't have anything else in here. Okay, so what I'm going to show you here is basically something that we call as the orthogonality of these characters in here. But it basically starts with this orthogonality of matrix elements. Right, it's basically this relationship. So we have 1 over the order of the group in here, so sum over the groups. And then I just write down some certain particular matrix elements of representations in here. So that matrix element is complex conjugated. The other matrix element is not complex conjugated. But I just take 2 different matrix elements. And on the right-hand side, I have delta mu, delta pi, delta pq and delta ij here, divided by the dimension d mu of the representation. Let's just remember this. Okay, so what we do is we just take p to be equal to I and q to be equal to j, and sum over sum over P and Q, right, on the left-hand side. So as a result, I'm going to do this thing in here, sum over P and sum over Q of U mu P P G star, U mu of Q Q G, right? And on the right-hand side, so we basically have a summation over P and Q of delta mu nu, delta PQ, delta PQ divided by D. In any case, if you do the summation over the right-hand side, we get delta mu. I'm not going to go over this. Here, I'm basically going to get the characters in here. So as a result, 1 over G times sum over the group elements of chi mu of G, complex conjugate chi mu of G. Okay. So that's the first relationship. So sometimes we actually use this relationship for certain proofs, for example. In that case, I consider the characters as functions of the elements of the group. But I would like to actually write this thing down as a summation over the classes. In that case, the sum is over a class. So for each class, since this expression is going to be the same, I would like to write Ni, the number of elements within the class I, multiplied with the character of the mute representation, complex conjugated, character of the mute representation, I, right? And that's delta mu. All right. It's the same expression. This is the second one is a little bit more simplified. So in practice, we actually use the second one. Okay. So this is called the orthogonality of the characters. It's like the orthogonality of two different vectors. But the things are a little bit complicated in here because of these extra factors of Ni and the number of elements of the group, the order of the group in here. So this makes things complicated. So for explaining this thing, I usually think of this like, think of this as a vector where the mute vector has an ith component, which is actually equal to the square root of Ni divided by the order of the group times chi mu I, right? Think of it like that, in which case I'm going to write down that relationship as, so V mu I complex conjugate V mu I, that's equal to delta mu. But I would then think of this as the dot product or the inner product of two vectors, delta mu. So in that way, this is actually an orthogonality of relationship, right? There's just some kind of complicating things in here, but you can easily think of this as an orthogonality relationship like that. Okay? And this is how we actually think of them actually. So when we say that the characters are orthogonal, this is what we mean, right? That's the relationship that we actually mean. So in real life, we never use this kind of constructions. I sometimes use this in here to explain some certain concepts in here. So then I talk about this thing. So I just construct a matrix. Forget about the matrix first, right? So let's say that C is the number of irreducible representations. Okay. So this then implies that these vectors in here, V1, V2, Vc is an orthonormal set of vectors in an NC-dimensional vector space. So the dimension is equal to the number of conjugate classes, because this is basically the number of possible I indices. So you can think of these as column vectors, perhaps. All right. So the number of such vectors is equal to C. So from here, then you deduce that the number of irreducible representations is less than or equal to the number of conjugate classes. So by using this mathematical relationship, orthogonality, this is what you can say. You can say more actually. You can show that these are actually equal to each other, but proving this a little bit more difficult. So as a result, I'm going to skip this, but in the notes you can find the proof that they are really equal, right? So that's the first rule in here, right? In representation theory, the number of irreducible representations is equal to the number of conjugacy classes. So let me write inverse. So the number of irreps of group G is equal to the number of conjugacy classes in the group G. Okay. So keep in mind that the conjugacy class is actually some kind of an abstract concept that you can define in the abstract group, right? I mean, it has nothing to do with matrices or anything like that. So we are somehow relating a property of the matrix representations to that abstract property of the conjugacy classes. Okay? So the number of conjugacy classes is equal to the number of irreducible representations. So if you think about it, for example, for the group S3, the permutations of 3 objects, the group S3 has order 6, right? It has 6 permutations in it. But we have said that there are like 3 conjugacy classes in there. 3 conjugacy classes. So this basically implies that there are 3 irreducible representations of the group S3. 2 of them are obvious. One of them is the trivial representation, and the other one is the signature. It appears that there's some kind of a non-trivial 2-dimensional irreducible representation as well, right? So S3 is going to be a nice example that we are going to work on for explaining some certain things. So, I mean, this is one of the things that we can say. Okay, so that's the first rule. Second rule is this. I have defined these matrices in here. Just think of it like that. I just construct a matrix, a square matrix B, by just writing all of these vectors like that, right? So think of these as column vectors. I write down all of these column vectors and then construct a square matrix, right? So the idea in here is this, all right? So V is basically a unitary matrix because of the fact that the columns of V is an orthonormal basis, right? Orthonormal basis. So once we have said that number of number of irreps is equal to the number of conjugacy classes, this is a square matrix, and because of the orthogonality of the characters, the columns is an orthonormal basis. Okay, therefore this is unitary. Therefore, I can say that the rows of V is an orthonormal basis. Orthonormal basis, which gives us a different relationship. Okay? But I mean, consider these elements and just do the same kind of an expression, and then you get a different relationship. So you can actually think of it like that. Let's see, V dagger V is equal to I is the orthogonality of the characters. And this basically implies that VB dagger is equal to identity. But this gives us a different relationship in terms of the characters, that where the summation is actually is done in over a different index. Okay. That's what I'm going to do next. So yeah, I'm just going to do this in short. Let's see. We were actually doing the summation. Yeah, first of all, let me write this thing down. So that's 1 over G Ni chi I mu complex conjugate chi I mu. So that's delta mu. So that's the orthogonality characters. Now I'm going to do a summation where the summation is now in terms of the irreducible representation index, right? Where phi mu I, complex conjugate, phi mu j, right? I'm doing this summation, and the result is delta ij, sorry, the order of the group divided by ni times delta ij, right? And that's called the completeness. Okay. All right. And in reality, of course, we actually use both of these relationships from time to time. So just keep this in mind. So both of them are really useful. So basically, you can check the unitarity of a matrix by just doing thinking of the thinking about the columns or by thinking about the rows. Right? That's essentially what it is. In any case, there's this another thing in here. So let's say that A from G to, I don't know, again, matrices, I don't need to specify the dimension. Any representation. Okay. And let's say that A is equal to M1U1 plus M2U2 plus dot, 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 dot. The last one is MC, right? Be a decomposition. Okay. Just remember that this decomposition is actually a shorthand for this one, right? U is a direct sum of U1 plus U1 plus so on, U1, but the U1 appears M1 times plus U2 and so on. So the U2 appears M2 times and so on, right? This is just a shorthand, right? Because we need to use these kind of shorthands, obviously. In any case, so it's a decomposition. So therefore, this implies that the character of A is equal to a sum over n mu phi mu of G. Okay. Let's just remember this. So I'm not going to take this as a box, but think of this like that, right? You can think of chi mu, the character, as a function, but we have said that it can also be considered as a vector, for example. I have shown how I can think of this as some kind of a column vector, actually. In any case, so this is actually a linear combination. So the character of A is actually a linear combination of the characters of the irreducible representations. Okay, so that's the first thing. Next thing is that, well, these are orthogonal. They are perpendicular to each other. And by using some certain rule, you can also say that they are normalized, right? Which means I can find these coefficients by a very simple inner product thing, actually. Okay, there are two calculations that I'm going to do. So first of all, this calculation. So I'm going, let's just remember this expression here. This expression. That's basically what I'm going to do. Or you can actually think of it like this expression here. The summation is either over the group elements or the classes, doesn't matter which one, but in practice, we actually do the summation over the class. So I'm going to write down that expression for the representation chi A, right? So I'm going to take the character of the chi, that representation, take modulus square, right, and then sum over the group elements. Okay, I can do this calculation in here, but I'm just going to write down the result in here. So that's basically the sum of the mu squared. It's quite easy to understand because these are normalized and perpendicular to each other. This is essentially Pythagorean theorem, right? if I write down a vector as a linear combination of the unit vectors where mu are the coefficients, then the length square of that vector is equal to the sum of the squares of these coefficients. That's essentially what it is, right? And so as a result, we get that. The proof, well, the proof goes like this, right? So 1 over g, so that expression, sorry, that's the order of the group. That expression, I can write this thing down as the complex conjugate of chi a multiplied with chi a. And then I'm going to write down this expansion for both of them. So as a result, this is 1 over g, and the sum over mu, and sum over the group elements of mu, and then chi mu star g, chi mu g, okay. And then we first carry out the g summation, in which case I'm going to get sum over, I mean, instead of this expression, I'm going to get delta mu. Sorry, there's no g left in here in that case, sorry, which is basically the sum of the mu squared. Okay. So in here, therefore, this is equal to m1 squared plus m2 squared plus mc squared. In any case, for any representation, this is actually an integer, which is 1 or bigger than 1, right? But this can actually be equal to 1 in only one situation. If one of these integers is equal to 1 and all the others are 0, right? I mean, let's just remember that each mu can be either 0 or a positive integer. If the sum of the squares of these integers is equal to 1, then that means one of them is equal to 1 and all the others are 0. So therefore, this can be equal to 1 only if the A is an irreducible representation. Okay. So that's the second rule. So a representation A, sorry, let's not confuse this A with the representation. A representation A is irreducible if and only if this expression is equal to 1. Okay, so as a result, if you found some representation and you suspect that it is, whether it is irreducible or not, and you can show that it is irreducible by carrying out that summation over the characters, and then, well, this will tell you that it is irreducible. Right? So that's the first thing. I mean, this is another rule, right? And there is a third rule in here. Okay, I can find this mu by doing some kind of a dot product, right? Think of it like that. So that chi a, considered as a vector, is just a linear combination of all of these vectors, chi mu. And if I take the dot product of, I don't know, think of it like that. But I have to take the complex conjugate in here. There's a slight complication in here. But if I take the dot product in here, then, so that's chi nu, sorry, chi nu, yeah, I mean, that's actually very complicated notation. So I have written down lowercase, a lower index in here and an upper index. Yeah, whatever. I mean, think of it like that, right? This dot product is either 0 or 1, and only one of the terms is equal to 1. So this actually gives us the coefficient in here. So that's the idea that we use. So as a result, I can express this mu coefficient in here by taking the dot product of that expression with the mu unit vector, all right? So that's the idea. So as a result, I'm going to write down this mu in here. So I'm not going to show this, but you can easily show it. So if I carry out that summation, right? Chi mu of g complex conjugate chi a of g, then I'm going to get the number of times the mu irrep appears in, right? So that's basically the number of times the irrep u mu appears in the decomposition of A. Okay. This also tells you that a given representation has a unique decomposition in terms of the irreducible representations. Because by just using this expression, I can find how many times a given irreducible representation appears in that decomposition. All right. Again, by using this kind of an idea to show that two representations are equivalent if they have the same character. Okay? But I'm going to leave that to you. You just have to understand how you can actually form some kind of a similarity transformation. All right. Okay. So yeah, I mean, these are the things that we actually use for actually doing the decomposition of a given representation. Usually in this process, we don't need to find the representation matrices explicitly. We need to compute, however, their characters, right? We have to somehow have a way of computing the trace of the representation matrices. Once we can compute the representation matrices, then we can find the decomposition and find how many times a given irreducible representation appears in the decomposition. Usually, we don't need to work explicitly with the matrices. Okay. So when time comes, we will talk about some physical applications, and in that case, we will kind of understand how we can actually use these representations. And there are only very few problems where we actually need the representation matrices explicitly. Otherwise, we don't need them. All right. So one thing that's the next thing is what we call is a regular representation. Right. So let's say that let G be a group, right? A finite group, obviously, again. So let's say that the order is equal to n, right? Order. The number of elements within the group is n. Okay. So let's just remember this theorem. I forgot whose name is associated with that theorem, but kind of tells you that the G can be, this group is actually isomorphic to a subgroup of Sn. Right? G is isomorphic. Sorry, isomorphic to a subgroup of Sn. Why? Because of this rearrangement lemma. So if you remember, if I take any group element, so G times G multiplied with all the group elements is going to give you the same group, but in a different order, if you remember. So that's basically G multiplied with, let's say, G1, Gn, let's say. These are the elements. So I basically get the same elements. Sorry, let me do this one more time. Same elements, but in a different order. So as a result, Gin, let's say, I can therefore think of the G as a permutation, that permutes the set of numbers from 1 to n into this set of numbers 1 to n. You can think of it like that, right? And this permutation is actually an element of Sn, right? And this kind of establishes some kind of an isomorphism between the group elements of that abstract group and the permutations in Sn. Okay. In any case, I have nothing to do with this. But just remember that each permutation can actually be expressed as a permutation matrix. Permutation matrix. Okay. So as a result, this group, for example, this group element would therefore be represented by a permutation matrix where the first column is 0, 0, 0, 1, 0, 0, 0, where the 1 appears in the I1 row, right? Basically, the first unit vector is converted into the unit vector in the I1 place, right? Or something like that, right? So in any case, so as a result, I can also think of this as a permutation matrix. In any case, that permutation matrix I'm going to call R of G, right? So as a result, from the group elements, I can write down the permutation matrix. So that's an n by n permutation matrix. So this is actually an homomorphism. Sorry about that, sorry. So it actually associates every element of the group with some permutation matrix. So it appears that this R is a homomorphism, so therefore this is a representation. Called the regular representation. Okay, whatever. So in any case, what we need to do is to compute the trace, the character of that representation, right? We would like to compute this. So first of all, that's something that's quite easy actually. First of all, the character of identity is equal to n, right? It's basically equal to the dimension because identity matrices, well, the identity matrix is its trace is equal to n. So therefore, that's equal to the order of the group. Okay, so that's for identity. Okay, and the character of R, character of any group element is basically the sum of the diagonal elements of the representation matrix. But just keep in mind that I mean these are basically either 0 or 1. Right? The matrix elements are 0 or 1, so that's an integer. But let's just remember that this is equal to 1. Sorry, Rij is, first of all, let me just say it like that, right? So Rij G is equal to 1 if G multiplied with the jth element gives you the ith element, right? Okay, I mean, let's just remember this. So that means a diagonal entry is equal to 1 if G multiplied with the ith element gives you the ith element, but this only happens if G is equal to identity, right? So as a result, if G is not equal to identity, all of these entries are equal to 0, so the trace is 0. Right? Let's say it like that. If G is an element which is not identity, then that's the character is equal to 0. But the character of identity is equal to the group. Okay. All right. So then I'm just going to use this relationship. Which one? This one in here. Or should I use it? Sorry about that. I'm not going to use that. So first of all, I'm going to use mu. So let's say that R is a decomposition of m1 times u1, m2 times u2, and so on. And mc times UC, where C is the number of classes, conjugate classes, and therefore it's equal to the number of irreducible representations. So mu is equal to 1 over the order of the group, sum over the group elements of chi mu of G, complex conjugate, chi mu, sorry, that's chi R of G. Okay. But this is easier to do because this is 0 for all elements except for identity. So therefore, this is 1 over G. The first term in here is chi mu of identity star in here. And this is basically equal to the order of the group. All the other elements are equal to, all the other terms are equal to 0. So they cancel each other. So this is equal to the dimension of the mute representation. So that's equal to d mu. So basically, mute irreducible representation appears d mu times, where d mu is the dimension of the representation. Okay, so that's the first relationship. The second one is this. I have said that sum over, sorry, let me first do this. Chi RG modulus squared is equal to the sum over mu and mu squared. Sorry, I'm going to use this again, the same thing, right? For identity, this is equal to the order of the group. So therefore, we have order of the group squared, and all the other terms are equal to 0. So the left-hand side is equal to the order of the group. And the right-hand side, well, basically, these are equal to the dimensions. So therefore, the order of the group is equal to the dimension, sum of the dimensions squared. Okay, so that's the last relationship. I mean, this is the one that's one of the important relationships. So sum of the squares of the dimensions of all irreducible representations is equal to the order of the group, right? That's one of the things, one of the important relationships that we actually use to construct the character table of the group. Okay, let me finish this in here. So starting with the next week, we are going to see how we can apply these to some physical problems.